Imagine that, somewhere on the other side of the Earth, a single button is pressed, a massive missile erupts from the ground and begins accelerating with unbelievable power. Within minutes, it is moving so fast that no aircraft on Earth could ever catch it. But something strange happens very quickly. The engines shut off. The missile stops firing its rockets, and from that moment it is no longer really flying. Instead, it is simply falling, following a gigantic arc through space that can carry it halfway around the planet in less than half an hour. Inside that falling object are nuclear warheads traveling faster than anything humans have ever built. And here is the disturbing part. Once this kind of missile has been launched, stopping it becomes incredibly difficult, not because of some mysterious futuristic technology, but because it obeys a few very simple laws of physics that were discovered hundreds of years ago. When an intercontinental ballistic missile is launched, the event begins with an explosion of controlled energy, powerful enough to lift a machine weighing tens of tons straight into the sky. The missile sits inside a reinforced underground silo or on a mobile launcher, waiting for a command that may come after years of silence. The moment that command arrives, the rocket engines ignite and an intense column of flame and exhaust erupts beneath the vehicle. For the first few seconds, the missile rises slowly, almost reluctantly, as if gravity is trying to pull it back to the ground. But the engines are designed to produce enormous thrust, and within moments, the missile begins accelerating rapidly upward through the atmosphere. The goal during this early stage is not accuracy, and it is not even reaching the target yet. The entire purpose of this phase is speed. Engineers call it the boost phase. And during these few minutes, the missile must gain enough velocity to send its payload on a journey that can cross entire oceans and continents. As the rocket climbs higher, its engines continue burning tremendous amounts of fuel. Modern ballistic missiles use multiple rocket stages, which means the missile sheds parts of itself during flight to become lighter and faster. After the first stage burns through its fuel, it detaches and falls back toward Earth, leaving the second stage to ignite and continue accelerating the missile even further. The acceleration during this phase is extraordinary. Within roughly 3 to 5 minutes, the missile reaches a velocity close to 7 kilometers per second. To understand what that means, imagine traveling from one side of a large city to the other in a single second. At that speed, the missile could cross an entire country in only a few minutes. No aircraft ever built can come close to this velocity. And even most defensive systems have almost no time to react while the missile is still accelerating upward. During these first minutes, the missile climbs through the thick lower layers of the atmosphere, cutting through clouds and rapidly thinning air as it approaches the edge of space. What makes this stage even more fascinating is that the missile is not trying to fly like an airplane. Airplanes need engines running constantly because they rely on air moving over their wings to stay in the sky. A ballistic missile works very differently. Its engines only need to operate long enough to give the missile an enormous initial push. Once that push is strong enough, the missile can continue its journey without any further propulsion. This is the same basic principle you see when someone throws a stone high into the air. The stone does not keep accelerating forever. It receives one powerful push from the throw. And after that, gravity and motion determine the rest of the path. Something surprising happens near the end of the boost phase. After those few intense minutes of acceleration, the rocket engines suddenly shut down. The missile has already reached the speed it needs. At this moment, the final stage of the rocket separates, leaving behind a smaller section that carries the payload. The roaring engines that launched the missile from the ground are now silent. From this point forward, the missile is no longer truly flying under its own power. Instead, it has become something closer to a projectile, a fast-moving object that has been thrown so powerfully that it will travel thousands of kilometers before falling back to Earth. By the time the engines stop firing, The missile is already traveling at extraordinary speed and climbing towards space along a carefully calculated path. The entire boost phase is surprisingly short, usually lasting only a few minutes. But those few minutes determine almost everything about the rest of the journey. Once the missile reaches this speed and altitude, it becomes dramatically harder to intercept because it is already moving faster than most defense systems can respond to. In other words, the moment the missile leaves the ground is also the moment the clock begins ticking. Within just a handful of minutes, the weapon has transformed from a stationary object into one of the fastest machines humans have ever built. Already racing toward the edge of space with enough momentum to cross half the planet. After the rocket engines shut down and the boost phase ends, something surprising happens. The missile stops behaving like a rocket and begins behaving like a projectile. From this moment forward, the weapon is no longer pushing itself through the sky with engines and fuel. Instead, it simply continues moving because it already has enormous momentum. The missile has been given such a powerful push during launch that gravity alone will guide the rest of its journey. This is why intercontinental ballistic missiles are called ballistic. They follow a ballistic trajectory, which is the same type of path that a thrown object follows when it moves through the air. To understand this strange type of travel, imagine throwing a stone across a field. The stone leaves your hand, climbs upward for a short moment, slows down as gravity pulls on it, and then begins falling back toward the ground. That curved path through the air is a ballistic trajectory. Now imagine throwing that stone thousands of times harder than any human possibly could. If the stone were given enough speed, it would travel incredibly far before gravity could pull it down again. In fact, if it were thrown fast enough, the stone could travel so far that it might land hundreds or even thousands of kilometers away. An ICBM works in exactly this way, except the scale is enormous. Instead of traveling a few dozen meters like a thrown stone, the missile travels across continents and oceans. The rocket engines provide a brief but extremely powerful push that launches the payload upward and forward at extraordinary speed. Once that push is complete, the rest of the flight is controlled almost entirely by physics, specifically gravity and motion. The missile climbs higher and higher along a giant arc that carries it far above the surface of the Earth. During the middle portion of the journey, the missile actually leaves the atmosphere and enters space. The altitude reached during this phase can exceed 1,000 kilometers above the planet. At this height, the sky is completely black and the curvature of the Earth becomes clearly visible. The vehicle that once looked like a roaring rocket during launch is now a silent object gliding through the vacuum of space. Because there is almost no air resistance at this altitude, nothing slows the missile down significantly. It continues forward at tremendous speed, following the curved path that was determined during the launch phase. This part of the journey is known as the mid-course phase, and it is the longest portion of the missile's flight. For most of the trip, the payload simply coasts through space, moving along a giant arc that stretches across the planet. The missile is not steering like an airplane, and it is not firing engines to adjust its direction. Its path was calculated long before launch, using mathematics that predict exactly how gravity will shape the trajectory. Once the missile reaches space, the laws of motion take over, and the path unfolds almost exactly as predicted. What makes this travel method so unusual is that the missile is not flying toward its target in a straight line through the atmosphere. Instead, it briefly leaves the planet, travels through space, and then eventually falls back toward Earth. From the side, the entire path looks like a massive arc stretching from one continent to another. The missile rises from the ground, climbs far above the atmosphere, travels across space, and then begins descending again thousands of kilometers away. This strange path is one of the reasons ballistic missiles are so difficult to stop. For much of their journey, they are not even inside the atmosphere where traditional air defense systems operate. Instead, they are moving silently through space at extremely high speed. By the time the missile begins its descent back toward Earth, it has already covered most of the distance to its target. The most fascinating part of this system is how simple the underlying physics really is. The missile is not relying on mysterious futuristic technology during this phase. It is simply following the natural behavior of objects moving under the influence of gravity. The same principles that describe a stone thrown through the air also describe the path of a missile traveling halfway around the world. The difference is not the physics itself. The difference is the scale, the speed, and the enormous distances involved. Once the missile has completed the boost phase and entered its long arc through space, another problem begins to appear, and this problem is speed. The velocity reached during launch is not just impressive. It is terrifying from the perspective of defense systems. A typical intercontinental ballistic missile travels at roughly 7 kilometers every second. That number is difficult to imagine because nothing in everyday life moves anywhere near that fast. At that velocity, the missile could cross an entire large city in less than a second. In only 1 minute, it can travel farther than many countries are wide. When people hear that a ballistic missile can travel across the planet in about 30 minutes, it sounds dramatic, but the true meaning of that number becomes clearer when you consider how quickly the missile is actually moving during every second of its flight. Speed changes the entire problem of defense. If an aircraft approaches a country's airspace, radar systems can detect it from far away, and military forces often have plenty of time to react. Fighter jets can be launched. Tracking systems can calculate the aircraft's path. And interceptors may attempt to stop it before it reaches its destination. Even cruise missiles, which are designed to fly low and fast, still travel within the atmosphere at speeds that allow some time for reaction, but a ballistic missile is operating in an entirely different category of motion. When something is traveling several kilometers every second, the timeline for response becomes extremely short. Consider what must happen if a defense system tries to stop a ballistic missile. First, the launch must be detected. Satellites and early warning radars are designed to watch for the intense heat signature produced by rocket engines during the boost phase. Once that signal is detected, computers begin calculating the trajectory of the missile. They must determine where the missile is going and how long it will take to arrive. This analysis has to happen almost immediately because every second that passes means the missile is moving dozens of kilometers closer to its destination. Even after the trajectory is predicted, the defenders still face a severe challenge. Interceptor missiles must be launched toward a target that is already traveling at extreme speed. But the interceptor itself also requires time to launch, accelerate, and reach the altitude where interception might occur. During this period, the incoming missile continues moving rapidly along its path. The window of opportunity to intercept the object is therefore extremely narrow. In many cases, only a few minutes exist between the moment a missile is detected and the moment it begins descending back toward the atmosphere. The speed problem becomes even more intense during the final stage of the missile's journey. As the warhead re-enters the atmosphere and falls back toward Earth, gravity begins pulling it downward with increasing force. Instead of slowing down, the warhead often maintains extraordinary velocity while descending toward its target. In many cases, it can still be traveling at several kilometers per second during this phase. At that speed, the warhead crosses huge distances in only moments, leaving almost no time for additional defensive actions. To understand how extreme this situation is, imagine trying to hit an object that is moving faster than any aircraft ever built, while it is also thousands of kilometers away. The defensive system must predict exactly where that object will be at a specific moment in the future and launch an interceptor to meet it at that precise point in space. If the timing is even slightly incorrect, the target will already have moved far beyond the interception point before the defensive missile arrives. This is why speed is one of the most important reasons ballistic missiles are so difficult to stop. The entire journey from launch to impact may last less than half an hour. But within that short period, the missile is traveling at velocities that compress time for everyone trying to respond. Decision makers must analyze data, confirm the threat, and determine a response in only a few minutes. Defense systems must launch interceptors almost immediately after detection. Every part of the response must move quickly because the missile itself is moving at a pace that leaves almost no room for delay. The terrifying reality is that physics does not allow these missiles to move slowly once they have been launched. The same momentum that allows them to travel across continents also ensures that they will remain incredibly fast for most of their journey. And when an object is traveling thousands of meters every second, time itself begins to feel like the rarest resource available to anyone trying to stop it. Up to this point, the journey of a ballistic missile already seems difficult enough to stop. The missile launches with enormous acceleration, climbs into space, and travels across the planet at several kilometers every second. But modern missile technology introduces another complication that makes interception even harder. This complication is known as MIRV, which stands for Multiple Independently Targetable Reentry Vehicles. The name sounds technical, but the idea behind it is surprisingly simple. Instead of carrying one warhead, a single missile can carry many. To understand why this matters, imagine a missile traveling through space during the middle portion of its flight. After the boost phase is complete, the rocket stages have fallen away and only the payload section remains. Inside this section is something called a post-boost vehicle, sometimes described as a small maneuvering platform. This platform contains several nuclear warheads and a guidance system that can slightly adjust its orientation while it travels through space. At this stage, the missile has already reached its enormous velocity and is following the giant arc that will eventually carry it back toward Earth. At a certain moment during the mid-course phase, the post-boost vehicle begins releasing its payload. Instead of dropping everything at once, the platform carefully positions itself and deploys the warheads one by one. Each warhead is placed onto a slightly different path that will lead to a different target. One warhead may be directed toward a military base, another toward a command center, and another toward a different city, hundreds of kilometers away. In other words, one missile can suddenly become many independent weapons traveling through space at extreme speed. This technique dramatically increases the destructive potential of a single missile. A launch that once carried one warhead can now deliver several. Some modern systems are capable of carrying 5, 8, or even more re-entry vehicles inside a single missile. When the payload platform finishes deploying them, the warheads continue traveling along their separate trajectories. From that point forward, each one behaves like its own ballistic object, descending toward its target at enormous speed. The effect on missile defense systems is significant. Intercepting one incoming object is already a difficult challenge because of the extreme velocities involved. But when a single missile divides into multiple warheads, the defensive system must now track and intercept each one individually. Instead of focusing on a single target, radar and guidance systems must monitor several fast-moving objects simultaneously. Each of these objects may be traveling on a slightly different path, requiring separate interception attempts. This multiplication of targets changes the balance between offense and defense. A country launching the missile only needs to send one rocket into space, but the defending side may need multiple interceptor missiles for each incoming warhead. In some cases, several interceptors might be launched at the same target to increase the chance of success. As a result, a single attacking missile can force defenders to expend a large number of defensive weapons in a very short time. There is also another subtle advantage to this design. Because the warheads separate in space during the mid-course phase, they may spread out across a wide region before re-entering the atmosphere. By the time they begin their descent back toward Earth, they may be hundreds of kilometers apart. This means defensive systems must attempt to intercept them across a large area rather than at a single point in the sky. From a technological perspective, the MIRV concept is remarkably clever. It takes advantage of the fact that once the missile reaches space and gains enormous momentum, relatively small adjustments can send objects onto very different trajectories. By carefully releasing warheads in sequence, the payload platform can transform one missile into a cluster of independent threats. Each warhead continues its silent journey through space. Following the curved path determined by physics and gravity, the result is a system that complicates defense in a profound way. Instead of confronting one incoming object, defenders may suddenly face several high-speed warheads approaching different targets at the same time. What began as a single launch becomes a network of separate threats descending toward Earth, all created from one missile that left the ground only minutes earlier. Even after understanding the speed of a ballistic missile and the ability to release multiple warheads, there is still another problem that makes interception far more complicated. This problem appears during the long mid-course phase when the warheads are traveling silently through space. At that moment, the missile system can introduce something called decoys. The idea behind decoys is surprisingly simple, but its effect on missile defense can be extremely powerful. Imagine a defense radar trying to track an incoming ballistic missile. The radar sends out signals and receives reflections from objects moving through space. These reflections allow computers to determine the position and motion of the incoming targets. In theory, the system should identify the warheads and direct interceptor missiles toward them. But the difficulty appears when the radar begins seeing many objects instead of just a few. Among the real warheads traveling toward Earth, there may also be a cloud of additional objects that look almost identical on radar screens. These additional objects are the decoys. They are intentionally released along with the real warheads during the mid-course phase of flight. In the vacuum of space, decoys can behave in ways that make them very difficult to distinguish from actual warheads. Some decoys may be lightweight metallic balloons that reflect radar signals strongly. Others may contain materials designed to mimic the radar signature of a real re-entry vehicle. When radar systems scan the region of space where the missile payload has separated, they may suddenly detect a large cluster of objects all moving at similar speeds and along similar paths. To a computer analyzing radar data, these objects can appear almost identical. Each one produces a reflection that could represent a real warhead. The defense system must decide which of these objects are the true threats and which are simply distractions. That decision has to be made quickly because the objects are still traveling at several kilometers every second. The defenders do not have the luxury of long analysis. They must determine where to aim interceptor missiles while the cluster of objects continues racing toward Earth. The difficulty becomes clear when you imagine the situation from the perspective of the defense system. Instead of tracking a single incoming warhead, the radar may detect 10 or 20 objects moving through space together. Some of these objects are real nuclear warheads that will survive re-entry and reach their targets. Others are decoys that exist only to confuse sensors and waste defensive resources. The radar cannot easily tell them apart because in the vacuum of space there is very little difference in how these objects move. On Earth, air resistance can reveal important clues about an object's weight and shape. A light balloon and a heavy metal object fall differently through the atmosphere because air slows them down in different ways. But in space, there is almost no air at all, Without air resistance, light decoys and heavy warheads can drift along very similar trajectories. Both continue moving forward with nearly the same velocity they had when they were released to a radar system observing them from thousands of kilometers away. They may appear nearly identical. This situation creates a difficult dilemma for defense planners. If the system launches interceptors toward every detected object, it may quickly run out of defensive missiles. But if it attempts to ignore some of the objects, it risks allowing a real warhead to pass through the defenses. The attacking side only needs to introduce enough uncertainty to overwhelm the decision process. By mixing real warheads with convincing decoys, the missile system forces defenders to solve a complex identification problem under extreme time pressure. The decoy strategy, therefore, turns the missile defense challenge into more than just a matter of speed and trajectory. It becomes a problem of information. The defense system must figure out what it is actually seeing in space before it can attempt to stop it. But the cluster of objects was specifically designed to make that task as difficult as possible. As the warheads and decoys continue traveling along their arc toward Earth, the defenders must decide where to commit their limited interceptors. Every decision happens while the objects are moving at extraordinary speed and the time remaining before re-entry grows shorter. In this way, the decoy problem adds another layer of complexity to an already challenging situation, making the task of stopping a ballistic missile even more uncertain. By the time a ballistic missile has released its warheads and possible decoys into space, the defenders face one final and extremely difficult task. They must try to intercept an object that is traveling at enormous speed and destroy it before it reaches its target. On paper, the idea sounds straightforward. Detect the incoming warhead, launch a defensive missile, and intercept the threat somewhere along its path. But in reality, the challenge is far more complicated than it appears. To understand the difficulty, imagine two bullets fired toward each other from a great distance. Each bullet is moving incredibly fast, and both are traveling along very precise trajectories. Now imagine trying to arrange their paths so that they collide in midair, even if you know the exact speed and direction of both bullets. Achieving that collision would require perfect timing and extraordinary precision. Missing by even a small margin would mean the bullets simply pass by each other without contact. This comparison is often used by engineers and defense analysts because it closely resembles the problem faced by missile defense systems. When an interceptor missile is launched, it must travel toward a predicted point in space where the incoming warhead is expected to be at a specific moment in time. The interceptor does not simply chase the warhead from behind. Instead, it is guided toward a calculated interception point far ahead along the warhead's path. The entire process depends on precise predictions of motion and extremely accurate guidance system. The interceptor itself must accelerate rapidly after launch. Its engines push it upward through the atmosphere and toward the region of space where the collision is expected to occur. During this time, onboard sensors and ground-based radar systems continuously update the interceptor's guidance system. Small adjustments are made to its trajectory so that it remains on course for the interception point. Meanwhile, the incoming warhead continues traveling at several kilometers every second, closing the distance toward Earth. In many modern missile defense systems, the interceptor does not rely on a large explosive warhead to destroy the incoming threat. Instead, it uses what is known as a kinetic kill vehicle. This device destroys the target purely through the energy of the collision itself. When two objects moving at extremely high speed collide, the energy released can be enormous. The kinetic kill vehicle is designed to strike the incoming warhead directly, transferring enough energy on impact to destroy or disable it. This method requires incredible accuracy. The interceptor must guide its kill vehicle to a point where it will physically collide with the warhead. If the interceptor passes even a few meters away, the collision will not occur and the warhead will continue along its path. Considering that this interaction is happening in space at velocities of several kilometers per second, the margin for error becomes extremely small. Another difficulty comes from the fact that the interception must occur within a limited window of time. The incoming warhead is traveling along its arc toward Earth, and the opportunity to intercept it exists only during certain portions of that journey. If the interceptor is launched too late, the warhead may already be descending into the atmosphere, where interception becomes even more difficult. If it is launched too early without accurate tracking information, it may miss the predicted collision point entirely. Guidance systems attempt to solve this problem by constantly updating calculations during flight. Radar stations track the incoming objects and transmit new information to the interceptor as it travels. The kill vehicle uses onboard sensors during the final moments of approach to refine its aim and guide itself toward the target. These adjustments occur rapidly because the closing speed between the interceptor and the warhead can be extremely high. Despite these advanced technologies, the challenge remains fundamentally rooted in physics and timing. Both objects are moving incredibly fast. Both are traveling across vast distances, and both must arrive at exactly the same point in space, at precisely the same moment. Achieving this requires extremely sophisticated tracking systems, advanced guidance computers, and a great deal of careful planning. This is why missile defense is often described using the phrase, hitting a bullet with another bullet. The interceptor must collide directly with a target that is already traveling faster than most vehicles humans have ever built. The entire event unfolds in only a few minutes and across thousands of kilometers of space. Even with modern technology, the task remains one of the most demanding challenges in aerospace engineering. After looking at every stage of a ballistic missile's journey, from launch to spaceflight to the release of multiple warheads and the challenge of interception, a deeper question begins to appear. Why is this type of weapon so difficult to stop in the first place? The surprising answer is that the missile is not relying on some mysterious or exotic technology during most of its flight. Instead, it is relying on a few extremely simple principles of physics that have been understood for centuries. Once these principles come together in the right way, they create a system that becomes extraordinarily difficult to interrupt. The first principle is momentum. During the boost phase, the rocket engines give the missile an enormous amount of speed. Once the engines stop firing, that speed does not simply disappear. According to the laws of motion, an object that is already moving will continue moving unless a force acts to stop it. In the near vacuum of space, there is almost nothing that can slow the missile down. There is no thick air to create drag, and there are no obstacles along its path. The missile simply continues moving forward with the momentum it gained during launch. The second principle is gravity. Gravity pulls everything toward the Earth, but it does so in a predictable and consistent way. Engineers take advantage of this predictability when calculating the trajectory of a ballistic missile. By choosing the correct launch angle and velocity, they can send the payload along a curved path that carries it far above the planet before gravity slowly bends that path back toward the surface. The missile does not need engines during this part of the journey because gravity itself helps shape the path. The weapon is essentially following a giant arc determined by the same force that causes a thrown stone to fall back to the ground. The third principle is energy. When the missile is launched, it carries an enormous amount of kinetic energy because of its high velocity. Kinetic energy increases dramatically as speed increases, which means that objects moving at several kilometers per second possess extraordinary amounts of energy even if they are relatively small. This energy makes the warheads extremely destructive and also makes interception difficult. Any interceptor must reach similar speeds in order to collide with the incoming object. Matching that level of energy requires powerful rockets and extremely precise timing. These three simple ideas, momentum, gravity, and energy, combine to create the system we call a ballistic missile. Once the missile has been launched and given its initial push, the rest of the journey is largely controlled by these natural laws. The missile climbs into space, coasts along a massive arc across the planet, and eventually falls back toward Earth with tremendous speed. Each stage of the journey is predictable in theory, but extremely difficult to interrupt in practice because of the distances and velocities involved. What makes this situation especially fascinating is that the underlying science is not new at all. The basic equations that describe these motions were developed hundreds of years ago when scientists first began studying how objects move under the influence of gravity. The same principles that explain the path of a cannonball or a stone thrown into the air can also describe the flight of a missile traveling halfway around the world. The physics is identical. The only difference is scale. Human technology has simply taken these basic laws and applied enormous power to them. Rockets provide the initial energy needed to push the missile into space. Guidance systems calculate the exact trajectory required to reach distant targets. But once the missile has reached the correct speed and direction, nature itself takes over. Momentum carries the object forward. Gravity bends its path across the planet, and energy ensures that it continues moving with incredible velocity. This is the reason ballistic missiles are often described as almost unstoppable once they are launched. It is not because they possess magical technology or impossible capabilities. It is because they take advantage of some of the most fundamental rules governing motion in our universe. When those rules are combined with powerful rockets and precise engineering, the result is a weapon that moves with such speed and predictability that stopping it becomes one of the most difficult challenges in modern defense. In the end, the story of ballistic missiles is not only a story about military technology, it is also a story about how the simplest laws of physics can produce outcomes of enormous consequence. The same natural principles that guide planets through space and cause objects to fall back to Earth can also guide a machine across half the world in less than an hour. And once that journey begins, those laws continue operating exactly as they always have, indifferent to the intentions of the people who set the process in motion.